Okay, in order to fully understand the plane waves, we need to be able to define the magnitudes. So the magnitudes that we are interested in are E, X incident, E, X reflected, E, H, Y incident, and H, Y reflected. Let's first work on the relationship between these two fields. There's a simple relationship that says the magnitude of the magnetic field is equal to the magnitude of the electric field divided by eta, where eta is the characteristic impedance of the region in which we're analyzing our fields. So if this is H incident, this is E incident. If this is H reflected, this is E reflected. This is eta in region number 1 if we're looking at the field in region number 1. Eta is like Z naught when we are analyzing transmission lines. It serves much the same function. Its units are in ohms, just like they were with Z naught. Eta is the square root of mu over epsilon if we have a lossless region, and it's the square root of mu over sigma plus j omega epsilon if we have a lossy region. Right here sigma is non-zero. Oh, and there's also a j omega up here. Again, the units of this are in ohms. For free space or air, this is 377 ohms for eta in air. So now we know the relationship between the electric field and the magnetic field for here, and the electric field and the magnetic field here. If we are given the incident electric field, we can find the incident magnetic field. If we're given the incident reflected field, we can find if we're given the electric reflected field, we can find the magnetic reflected field. The next thing that we want to be able to analyze is how we go between the incident and the reflected field, and you've already seen that. The electric field that's reflected is the reflection coefficient times the incident field in both of these cases. Now there's a very important factor here. In this case right here, we have region number 1 and region number 2. We're going to be able to find the reflection coefficient in much the same way we did with transmission lines. If we consider this to be Z naught, or the transmission line in which our propagation is taking place, and this is Z load, we can write the reflection coefficient right here as ZL minus Z naught over ZL plus Z naught. And that is a unitless ratio. In this case, if ZL is real and Z naught is real, this would be strictly real. But in general, these are complex numbers, and so gamma is complex. It has a magnitude and a phase. This is what we would have done with transmission lines. Up here with regions, we do this as eta 2 minus eta 1 over eta 2 plus eta 1. I think it's easier to remember these as load and origin, so just change this to load and origin. So that gives us a reflection coefficient. I want you to notice where this reflection coefficient is. Right here, this is the reflection coefficient that we would have calculated right here, right where exactly where this load is. In the case of the two regions, the reflection coefficient that we calculated is right here. That's where the wave starts moving back to the left. The reflection coefficient is calculated here. It is not calculated here. It is not calculated here, and it's not calculated over here. The reflection coefficient is calculated right at this point. Now, if I know the incident electric field, I can then know the reflected electric field. If I know the incident electric, I can find the incident magnetic, and if I know the reflected electric, I can also find the reflected magnetic. So we've been able to analyze all of the values that we need. We could plug these into the equations that we currently have for a region that has only two materials. That's assuming that this material is infinitely long, or it's long enough that the wave dissipates or is fully attenuated before it gets to the other side. But the next thing that we want to analyze is something that has multiple layers. For instance, instead of just having air and tissue simulant material, we now want to analyze a region that has air, skin, fat, muscle, bone, and so on. So we want to be able to handle multiple regions. The value that we will need to find is this reflection coefficient. So let's do that next.